succès dans mes affaires, j'ai du succès dans mes amours, je change souvent de secrétaire. J'ai mon bureau en haut d'une tour, où je vois la vie à l'envers, je contrôle mon univers. Je passe la moitié de ma vie en l'air, entre New York et Singapour, je voyage toujours en première. J'ai ma résidence secondaire dans tous les îlots de la terre, je peux pas supporter la misère. Moi, les heureux, je suis pas heureux mais j'en ai l'air. J'ai perdu le sens de l'humour, j'ai le sens des affaires. J'ai réussi, j'en suis fier, au fond je n'ai qu'un seul regret, je fais pas ce que j'aurais voulu faire. Est-ce que tu veux ton Dieu, dans la vie on fait ce qu'on veut, à ce qu'on veut. J'aurais voulu être un artiste.
Morning.
Pour pouvoir faire mon numéro. Quand l'avion se pose sur la piste, à Rotterdam ou à Lyon, j'aurais voulu être un chanteur. Pour pouvoir crier qui je suis. J'aurais voulu être un auteur pour pouvoir inventer ma vie. Pour pouvoir inventer ma vie. J'aurais voulu être un acteur pour tous les jours changer de peau et pour pouvoir me trouver sur un grand écran en couleur, sur un grand écran en couleur. J'aurais voulu être un artiste pour avoir le monde à refaire, pour pouvoir être un anarchiste et vivre comme un millionnaire, vivre comme un millionnaire. J'aurais voulu être un pour pouvoir dire pourquoi j'existe.
Morning, everyone. Yeah, so the final is 8 questions. Don't let that worry you. It's doable in 3 hours. And that's what's important. It is cumulative, so it covers the whole course. Questions? How are we doing with the with polar coordinates? Shall we try another example? Before we do so, today's song brought to you by Claude Dubois. The title was The Blues to Businessmen. Off the rock opera Starmania, written by Luc Plamondon. Let's do one more. Consider the following. We are asked to find the area Morning, everyone. So consider this. Let's take a moment to graph these. Right, we're looking for the area inside both. I mean, this is meaningless if we don't have the graph. So let's graph. Right, let's graph the first one. You know, I'm not gonna graph cosine theta. After this course, we have finished the calculus textbook. If you have the big one, well, or if you have the other one, it doesn't matter. The answer is no. No, there's still advanced calculus, calculus 4, where you'll do the remainder, namely calculus on surfaces. So it's another way of extending the notion of the integral over surfaces instead of just domains in the xy plane. Maybe we'll talk about it briefly at the end. Speaking of the end, I have been informed that Monday is our last day. I thought it would go up until Tuesday, but apparently Tuesday is a study day. And there are issues with the final exam. The exam office was not aware of faculty regulations that force exams worth more than 20% to have a 72-hour window. So they're working on that. So right now, the final exam schedule is a tentative one. It is subject to change. All right. So let's graph this. You know that cosine of 0 is 1, so this whole thing is going to start at 2. And then as theta increases, cosine decreases all the way to 0 at pi over 2, and then all the way to -1 at pi. So you know what this is going to look like, right? Cosine is decreasing all the way to 1 at pi over 2, and then decreases all the way to -1. So r is going to be 0 at pi. And then it increases back to 1, or back to 0, cosine does. So r increases back to 1, and finally back to 2. There it is. And if we consider this one, again, cosine of 0 is 1. 1 minus 1 is 0. So we're starting at 0. Cosine is decreasing, so the r is increasing all the way to 1 at pi over 2. And cosine keeps decreasing all the way to negative 1, so r increases all the way to 2 at pi. And then it does the same thing on the other side. So find the area inside both of these things. Obviously, we are looking for this area. Convinced? I mean, you can probably, well, first of all, I mean, there is obvious symmetry like this. So we can just calculate this one and multiply by 2. Secondly, there's probably, this part is probably the same as this part. We might not be 100% sure. Is it mandatory to graph during the exam? Well, you're not going to be able to figure out what part you want if you don't graph it. How would you know that this is what you want if you don't have the graph in front of you? There's no way. There's absolutely no way. So you have to graph. So you see, well, so first of all, if you can argue that there's obvious symmetry, but I mean, we're not 100% sure here. You should include the graph on paper. Absolutely. Absolutely. Otherwise, if you just give the setup, how did you come up with that? Did you get that from a forum? Did somebody tell you what's going on? You have to justify, and this is the justification. So you see this part right here, this is going to be, so first of all, we're just going to do the top half, and the bottom half is the same, so 1/2. And the integral, this part right here, has to do with the second function, right? This is realized in 0 to pi over 2. So 1/2, 0 to pi over 2 of 1 minus cos theta all squared. And then we're going to add this other half, which is the integral from pi over 2 to pi of the 1 plus cos. Now, we strongly suspect that these two halves are the same, but we didn't bother arguing. We'll just evaluate and we'll see. We have to do the first graph. Maybe, Sinbad, you're asking if you have to do the graph first, and then the answer is yes. Well, I mean, we noticed that these intersected at 1, right, on the y-axis, at 1 and minus 1, and that corresponded, well, I mean, in this part right here, this was realized in 0 to pi over 2, right? That's the second business here. When theta is pi over 2, this is 1, and we're right here. Similarly, this part corresponds to this to this function, to this graph, and when theta is pi over 2, you're right here, right? Cosine of pi over 2 is 0, so you're at 1, and then you decrease all the way to 0. So that's why it's important to graph so that you know what's going on. So how do we know both of these are equal? Well, you know how cosine behaves. And you know that whatever happened from 0 to pi, the same thing is going to happen in reverse. So that's why you know you have symmetry about the x-axis in both cases. So immediately this area is going to be the same as that one. The xy one is the important one. The xy one is the important one. So that's the one you want to include. I mean, of course, it's oftentimes very important to draw the r theta one and then do it from there, but you have a lot of experience with that now. So I jump right away to the xy. Let's set that up. The 2's and the 1/2's cancel out nicely. So this is 1 minus 2 cos plus cos squared plus the integral from pi over 2 to pi, 1 plus 2 cos plus cos squared. Integrate. So you see they are the same. As we might have suspected. Yeah, exactly. That's right. The high integral of 1 is theta. So maybe you're wondering, why is it 3 over 2? But how do we integrate cosine squared? You know cosine squared is 1/2, 1 plus cosine 2 theta. And then the 1/2 plus the 1 gives you the 3 over 2. Convinced? How are we doing? Very nice. How are we doing here? Questions? So you see this is the same as that, right? So this is the same as that, and this region was the same as that region. Very nice. Again, we probably could have made an argument that this was the same as that. But, there was, if you're not 100% sure, then don't do it and just evaluate the integral. All right. Sure. Consider this, r equals e to the theta. Can we graph that? Let's graph that for theta between 0 and pi over 2. When theta is 0, e to the 0 is 1. And you know what's happening to the exponential function, right? The exponential function is getting larger and larger and larger. So as theta increases, this is getting larger and larger. Well, I was saying 2 pi, right? So that we go once around, but you could continue, right? At 2 pi, we're here. E to the 2 pi is whatever, and again, this keeps going and going. Right? There's no reason to stop. Right? You've got this spiral happening. There it is. Oh, did I mention pi over 2? Sorry, I meant 2 pi. But let's ask ourselves, what happens going the other way? What happens for angles less than 0? Right? And if you have negative angles, then you have a 1 over. Right? I mean, you know the graph of e to the x. Right? You know the graph of e to the theta and the theta r plane, right? What we've just graphed is this business right here. But if we go the other way, what is happening to R? What is happening to e to the theta? Right? What is happening to e to the theta? It's getting closer and closer to, it's getting smaller and smaller, closer and closer to 0. So if we go the other way, these are getting smaller and smaller, closer and closer to 0, without ever reaching it. Isn't that nice? Spiraling infinitely close to 0, infinitely close to the origin. Very nice. And we can ask the question, if we just look at the 0 to pi business, if we just look at the 0 to pi business, we can ask, what is the area here? The area under the graph, which is equivalent, right, to, so that shaded area here is going to be 1/2 the integral from 0 to pi of e to the theta all squared. Which is 1/4 e to the 2 theta from 0 to pi, which is 1/4 e to the 2 pi minus 1. Here's a nice is there a specific polar equation for the Fibonacci spiral? The thing with the Fibonacci sequence is that it has this nice geometric formula. So I strongly suspect that if you just graph that, you're good to go. So it's not going to be, not so much, well, I guess if you just take the power to be theta, I'm going to suspect yes. Here's a nice exercise that I asked on last year's final exam. Show that Laplace's equation in polar coordinates becomes Aisha wants to know why we decided on 0 to pi, just for fun. I mean, we just as an exercise. No special reason. There it is. This is a very important exercise that everybody should do at least once in their life. So let's do it together. What is Laplace's equation? You'll remember that. So here, what's the idea? Z is some function of x and y, where x is r cos theta and y is r sine theta. Laplace's equation says that d squared z by dx squared plus d squared z by dy squared is equal to 0. This is Laplace's equation. So if you plug in the polar coordinates, let us evaluate d squared z by dr squared. Let us evaluate dz dr. Let us evaluate d squared z by d theta squared. What is dz dr? Well, you see, you have an r in both coordinates. This is just an application of the chain rule. To differentiate with respect to r, you have to differentiate with respect to the first variable times the derivative of the inside. So this is f1 of this whole thing. Let me rewrite it once, but I'm not going to rewrite it again. Times the derivative of the inside with respect to r. Plus the derivative of the second variable. Times the derivative of the inside with respect to r. Very good. So that's dz dr. Let's differentiate that a second time. In other words, differentiate this with respect to r. Absolutely. This equation is widely used in physics and differential equations and this and that. The functions satisfying Laplace's equation are extensively studied. It's a very nice result that if you have a function satisfying Laplace's equation on some domain, then the maximum and minimum are attained on the boundary. And you have a bunch of other properties as well. I said a domain, but I think it's really just a disk. Anyways, for sure on the disk, the max and min are attained on the boundary. You can prove that relatively easily. So differentiate this with respect to r. Now you see f1 still depends on r cos and r sine, and so does f2. So chain rule kicks in again. Even if there's a critical point inside the disk, the max and min are still going to occur on the boundary. That's the beautiful result. Because what happens is that the function at any point must be equal to the integral on the circle around that point. So that if a function, this implies that the maximum cannot occur at that point, it must occur on the boundary. If it's not constant, of course. So differentiate this with respect to r. So you see, you've got an r in both of these components. So that is f11. Now I'm going to stop writing that. So f11 cos theta times the derivative of the inside plus f12 cos times the derivative of the inside. And same thing for here. This is f21 times sine times the derivative of the inside plus f22 times sine times the derivative of the inside. Indeed, partly, right? The way the derivatives alternate between sine and cos is what makes this equation valid. We'll see that a lot of stuff cancels out. Yeah. dz d theta, right? Again, this is f1 times minus r sine plus f2 times r cos. And now when we differentiate a second time with respect to theta, you see that we now have a product. So product rule applies. Differentiate this one, leaving that one fixed. So minus r cos times f1 plus, we'll leave this one fixed and differentiate f1, getting f11 times minus r sine plus f12 times r cos. And similarly, the derivative of this is differentiate this one, so minus r sine, leaving f2 fixed, plus r cos, and we'll differentiate the f2 with respect to theta. What do we get? f21 times the derivative of the inside with respect to theta plus f22 times the derivative of the inside with respect to theta. It's a valid question. Taha brings up a good question. Can we assume F12 is equal to F21? And here's the thing. Sometimes you need to do that. Other times you don't. So let's wait until the end. If we need to make that assumption, we will. Let's just keep that possibility open and we'll adjust need be. So I've written it off now, but the question was asking us to look at d squared z by dr squared plus 1 over r dz dr plus 1 over r squared d squared z by d theta squared. So let's evaluate that for these three things that we have worked out. What is that? D squared z by dr squared, we have it right here. So this is f11 cos squared plus f12 sine cos plus f21 sine cos plus f22 sine squared. The dzdr, we had it here. So that is f1 cos plus f2 sine and d squared z by d theta squared is this business right here. What do we have there? So minus f1 r cos let me group this right here, minus f2 r sine, multiply that in, so we get a plus f11 r squared sine squared minus f12 r squared sine cos and these two terms, can I fit them in here? Let's try. Minus f21 r squared sine cos and f22 r squared cos squared. All right. All right. So observe, right? If we multiply the 1 over r squared into this, one of the r's cancel, and you're left with 1 over r f1 cos with a minus, and over here you've got a 1 over r f1 cos. So these things cancel out. Similarly, these two cancel out as well. Very good. f12 sine cos And if you multiply the r 1 over r squared, canceling well with this one, here you have a minus f12 sine cos. So this and this cancel out. And similarly, this one and this one will cancel out because they have the opposite signs. What does that leave us with? What does that leave us with? We have the f11 cos squared plus f22 sine squared. Right, these two terms are still there. And this is all gone. And what's left in here, if we multiply by 1 over r squared, we have f11 sine squared plus this term, f22 cos squared. And now, if you factor out an f11 here, you get sine squared plus cosine squared. And if you factor out an f22, you get sine squared plus cosine squared. So sine squared plus cosine squared is just 1. So this is f11 plus f22, exactly the left-hand side of Laplace's equation. And that is equal to 0. How are we doing? A nice exercise, right? Just a simple application of the chain rule. Why is this equal to 0? Well, that's Laplace's equation. How many people got full score on the question? Certainly 75% of the class. That's the beauty of this question. Either you know what you're doing and you get 100 because there's almost no thinking, or you don't know what you're doing and it's very easy to mark, because if you don't know what you're doing, then you don't do anything. Questions? Right? It's very nice. Very nice how. Yeah. All right. Let's move on. Let's move on to ask the question. Can we talk about you can expect this on the exam, absolutely. It's a standard question in all books. Any book you pick up that discusses the chain rule is pretty much going to have this question. And we covered the chain rule, so you should expect something like this, absolutely. mean, look, it seems overwhelming because you're seeing it now for the first time. After class, you're going to look at it again and try to do it without looking at your notes. It's just an application of the chain rule. You start with the equation they give you, right? dZdRr plus 1 over r dZdR plus 1 over r squared dZd theta theta. So you start with this, and you, right now, I'm not asking you to come up with that. That's not what's happening here. And that's a much more difficult question. Instead, I'm giving you this and telling you to verify that it's equal to F11 plus F22. Right? Coming up with that, sorry, there's this squared here. Coming up with that on your own would be a lot of work. Exactly. We're working backwards. We're working with the answer going back. Length of a polar curve. Let's go back to Cal 2. No, nobody's Laplace here, right? Nobody here is Laplace. So it's all good. Well, I mean, I shouldn't say nobody. I mean, we could have some geniuses on the other side of the screen, but let's just say I'm no Laplace. And that's all right. Back to Cal 2, when we were asking the question, what about arc length? How long is this curve? Remember how we introduced that? We said we were going to use a few straight lines, and we were going to use a few straight lines as an approximation to the length of the curve. Now, those straight lines can be seen as hypotenuse of right-angled triangles, where this is the change in x, and this is the change in y. And we absolutely, right? But Nicholas is giving us the final answer, but that's not what we're interested in here. Right? We're going to approximate the length by adding these straight lines, which can be viewed as hypotenuse of these right-angled triangles. And by the Pythagorean theorem, this hypotenuse is going to have length delta x squared plus delta y squared. So the length of each of these straight lines is exactly this. And we're going to add all of those up. And Nicholas gave us the answer we found in Cal 2. And if you remember, the issue here is that this is not a Riemann sum, right? I mean, we're missing a delta x to have a Riemann sum here. But we have one here, and we decided to pull it out and got Nicholas's result, which was very nice. Let's not do that here because we don't have x's and y's. We're working in polar coordinates. We're working in r and theta. So if you have some sort of polar curve, r as a function of theta, then what you really have is x and y in terms of theta. So I don't want to pull out a delta x. I would like a delta theta. So let me multiply by 1. Delta theta over delta theta. I'm multiplying by 1, I'm not changing anything. And now bring this delta theta inside. So we get delta x over delta theta squared plus delta y over delta theta squared with a delta theta outside. Now we have a Riemann sum. Now we have what we're looking for. And as delta theta gets smaller and smaller, this summation becomes an integral. This becomes dx d theta. This becomes dy d theta. D theta. But if x is this and y is that, then dx d theta. What is dx d theta? Dx d theta is f prime, right? I mean, it's a product there, so product rule applies. F prime plus f times the derivative of cos, which is negative sine, and dy d theta, same thing. So if you square those and add them together, what do we get? F prime squared cos squared. This times 2 to f prime sine cos. And this square plus f prime squared sine squared. This times 2. And this square. And you see what's happening, right? These cancel out. This plus this, when you factor that out, you get f prime squared times sine squared plus cosine squared, which is 1. And same here. So you get this nice arc length formula. If you have r as a function of theta, the arc length is going to be the integral of the square root of the derivative squared plus the original function squared. Why is this x? Convinced? How are we doing? Was the initial graph in x and y or r and theta? It was in r and theta, right? If r is given as a function of theta, let's take an example. Let's take an example. We are asked to find the length of the polar curve. It's the arc length of, well, I mean, here it is. I mean, there's always the x and y underlying, right? Because it's the graph in the xy plane. Right, and we graph this already, right? This is the exponential. Which looks like this. Oh, only the pi over 2, sorry. So this is e to the pi over 4. So we're looking for this length of the curve. Are the arc lengths of the same function graphed in r and theta and xy the same? It's a good question. It's a good question. And let's investigate with this example. Is this example going to do it? This example is probably going to be very difficult, if not impossible. Well, let's not suspect anything. I suspect, what do I suspect? I might suspect that they are. I don't know how to prove that. Let's evaluate this first, and then we'll talk about. So r prime is 1/2 e to the theta over 2, and the arc length is the integral from 0 to pi over 2 of the square root of your function squared, well, the derivative squared, plus the original function squared. Right, I'm using this formula. And I think we have the answer to our question, right? We have the answer to our question. So here, what is that? This is 1/4 e to the theta plus e to the theta. So this is 5/4 e to the theta, or √5/2 e to the theta over 2. Whose antiderivative is √5 e to the theta over 2 from 0 to pi over 2, which is just √5 e to the pi over 4 minus 1. Right? Now the question that arose was, if we graph that in the theta r plane, where r is e to the theta over 2, you know what that looks like, right? I mean, it starts at 1, and at pi over 2, it's e to the pi over 4, which kind of looks like this curve, but sideways. So it seems like the answers might coincide, but here, using Nicholas's formula, the arc length is the integral from 0 to pi over 2 of the square root of 1 plus the derivative squared, right? This is from 141. And this, well, the derivative of that is just 1/2 e to the theta over 2 all squared. Or, I mean, if you look at this, it's just this part plus 1, not plus this. And now we're in trouble. That's exactly what we're doing. And you see the issue, right? This part, so in our formula, this is the integral from 0 to pi over 2 square root of 1 plus f prime squared, as opposed to f prime squared plus the original f. So it's not the same. It's not the same immediately, right? In our case, this is always bigger than or equal to 1. In fact, it's always bigger than 1 at every point except 0. So this one here is going to be bigger than that one. Obviously. So there's our answer, even though we might be misled to believe that they're the same, they're not. So even though we didn't calculate this integral, it's obvious that this is less than the other one. A very interesting question though. I'd never given any thought to it. And I mean, of course, if they had been the same, I suspect somebody would have noticed it and pointed it out at some point, but now we see that they're not. Yes, exactly that, Aisha. This one here is in terms of r and theta, whereas this one here is the graph in the xy plane. And that's what's of importance to us. It's in the xy plane, not in the theta r plane. Very nice. Can we talk about tangent line for a moment? Wait, Taha, where did I lose you? I think Aisha's fine. Are you fine too? Let's talk about tangent line. Right? An obvious question. If we have a polar curve, again, in the xy plane, of course, right? So if we have a polar curve in the xy plane, what is, or can we work out the tangent line? Well, you know, in order to work out the tangent line, you need dy dx. That's all you need. You need the derivative and a point. But by the chain rule, dy dx is dy d theta. D theta dx. Right? Because the thetas just cancel out in a terrible abusive notation, but you're used to that. And by the implicit function theorem, this is 1 over dx d theta, assuming dx d theta is non-zero. And there you have it. dy dx is dy d theta divided by dx d theta. This is the slope of the tangent line. Well, if you have theta as a function of x, are we allowed to manipulate derivatives like that? Well, I'm suggesting, first of all, this is by the chain rule, the one variable chain rule from Cal 1. And this is from the implicit function theorem, again in Cal 1. And I mean, it relates these two things. right? I mean, it tells you that if you have theta as a function of x, you can solve for x as a function of theta as long as dx d theta is not 0. So that's what the implicit function theorem says. Let's take an example. We are asked to find the tangent line to all right, we're not going to graph this. Let's not graph it. But, I mean, you understand that, you know, I mean, you got something, some sort of curve. And at pi over 4, say, you have some point. And we're looking for the tangent line. This is, of course, everything is in the xy plane. So we see that dy dx is dy d theta, dx d theta, dx d theta, where x is r cos and y is r sine. But r is this. All of these are valid manipulations, right? Chain rule from Cal 1, implicit function theorem from Cal 1. We're good. I mean, I am making the assumption that dx d theta is non-zero, but that's it. The ends will justify the means here. And speaking of ends justifying the means, in the Laplace's equation example, let me point out, I mean, I should have done it back then, but we did not need to assume equality of the mixed partials. In some cases you do. Here in that case, everything canceled out nicely, so there was no issue. If we had needed to make use of the equality of the mixed partials, then you just state it. Assuming equality of the mixed partials, blah, blah, blah. Well, if dx d theta were 0, that might imply some vertical tangent line. So you'd want to check what happens there. Absolutely, you can assume equality of the mixed partials without proving anything, and just, I mean, you know, you would state in the context of equality of the mixed partials, we get the following. So what do we have here? Dx d theta, the derivative, it's a product, so product rule applies. Differentiate the first one, cos 3 theta times 3, leaving the second one fixed. Plus, leave the first one fixed. Differentiate the second one. Why don't I plug in right away the point when theta is pi over 4? What do we get? Cosine of 3 pi over 4 is negative 1 over root 2 times 3 times 1 over root 2. And this is 2 plus sine of 3 pi over 4 is positive 1 over root 2. And sine of pi over 4 is again 1 over root 2. So this is minus 3 over 2 minus root 2 minus 1 over 2. So minus 4. So minus 2 minus root 2. And dy d theta. Right, so first of all, non-zero, so everything is justified. And the derivative there. So dy d theta at pi over 4. We said this was 1 over root 2. So this is minus 3 over 2. Plus root 2 plus 1/2. So this is minus 1 plus root 2. And so that over that. Oh, there it is. There's always asking what happens if dx d theta is 0. So this method doesn't work. I mean, especially if you get a 0 over 0, we're in trouble. If you get a 0, if dy d theta wasn't 0, this would imply an infinite slope. In other words, really a vertical line happening. But if both are 0, then we're really in trouble there. And other techniques have to be employed. Exactly, and when this is in the xy plane, so there's only one tangent line. Absolutely. And so this is going to be the slope of your tangent line. So your tangent line, y equals your tangent line is this, and at pi over 4, 2 plus 1 over root 2 times 1 over root 2. And y is 2 plus 1 over root 2 times 1 over root 2. In other words, this is root 2 plus 1/2. So when all right. Yeah, so when x is this, y is that. I mean, I'm going to let you finish that up here. Thank you, Nicholas is giving us a simpler version. 4 minus root 3 minus 3 root 2 over 2. That still doesn't simplify very much, but still a lot of solving for b. I'm going to let you solve for that. Probably should have gone with a simpler example. Who knew? How did we get x and y? We knew we were dealing with 2 plus sine 3 theta. That was our curve, right? So x, which is r cos, so it's this times that, and we had theta at pi over 4. So just plug in pi over 4 into this one, and same for the y. You should simplify everything on the exam. Simplify everything, show your work. Questions? So how do these polar coordinates fit in to double integrals? Right? I mean, we saw that you could express complicated curves in simpler ways using polar coordinates. So that's going to be extremely useful in double integrals. The question arises though, right? When, I mean, let's go back to Cal 2 for a moment and suppose you wanted to evaluate this integral. You know what to do. This calls for a trig substitution. X equals sine theta. So that dx is cos theta, d theta. And you see, you have to evaluate your dx in terms of the new variable. Now imagine a scenario where you have a double integral dy dx. And suppose that you're going to make a transformation very similar to this, right? But now you have both x and y, where you're going to perhaps transform x and y into functions of other variables, u and v, functions of other variables u and v. Question: what is dy dx in terms of du dv? Right? In very much the same way where you had to express dx in terms of d theta, here we have dy dx. What is dy dx in terms of the new variables? Du dv. Well, I mean, what would we expect? Right? You might expect dx du, dx dv, dy du, and dy dv to play a role. In the same way that the derivative of x, right? This is dx d theta. In the same way that the derivative of x plays a role in the one variable case, you might expect all the derivatives to play a role in the two variable case. Theorem. If x is a function of u and v, and y is a function of u and v, right? So exactly what we did here. I'm just not introducing a g and an h. If x and y are functions of u and v, then dy dx is the absolute value of the Jacobian du dv, where j, the Jacobian, is dxy by duv, or dx du, dx dv, dy du, dy dv. So you see all four partial derivatives, all four first order partial derivatives play a role in as the Jacobian. Geometrically, what is really happening here? You have some domain in the x and y plane. What we're saying is that these small rectangles, right, dx, dy, we're transforming these into the UV plane. The Jacobian is the determinant. Exactly, right? It's the determinant that's where these straight lines, that's what the straight lines denote. What we're saying is when you make a transformation into the UV plane and get some new domain, the Jacobian compensates for the change in area. That's what the Jacobian does. The Jacobian compensates for the change in area. Questions? Well, now the obvious question that arises, what is the Jacobian of the polar coordinate transformation? So first of all, let's recall the polar coordinates. X is r cos, y is r sine. So the Jacobian is dx dr, dx d theta, dy dr, dy d theta. Let's work that out together. Dx dr is easily seen to be cos. Dx d theta minus r sine, dy dr, and dy d theta. Determinant, 2 by 2, you know the deal. This is r cos squared minus r sine squared. Factor out an r and you get cos squared plus sine squared, which is 1. And there it is. Jacobian is r. The Jacobian of the polar coordinate transformation is r. So when you make a polar coordinate transformation, when you switch to polar coordinates, you throw in absolute value of r. In most cases, you can make sure that r is positive, so you don't need the absolute values. But keep in mind, in the back of your head, that they're always there. Questions here? Shall we take a few examples? Question arises, do we only use this with polar functions or normal ones too? Normal ones. We'll see, we'll illustrate with this example. And that's exactly correct. dy dx is absolute value of r dr d theta. Let's illustrate everything with this example. This example will make everything crystal clear, I believe. let's start by graphing the domain. What do we have here? You recognize this as a circle centered at the origin of radius 2. Can we take a moment to appreciate that circle? Did I just ruin it now? Making it worse. All right. Circle of radius 2. First of all, we're restricting our attention to the first quadrant. X equals 0 is the y-axis. And y equals x. Thank you, Zoe. And y equals x. So that region enclosed by these three curves in the first quadrant is, of course, this region right here. All right. Everybody comfortable with that? Very well. So let's set up our integral. Forget polar coordinates. Forget it. And let's set up our integral. Dx dy or dy dx. First question. Do we want to set it up dy dx or dx dy? Fubini's theorem tells us we have that option. We can do whatever we want. So do we want to set it up dx dy or dy dx? You tell me. Right? If we dy dx is the way to go. Why? Well, if we set it up dx dy, let's think about setting it up dx dy. How does x vary? First of all, right, this is the increasing direction for x. X starts living here. The region starts there and ends there. For a while, right, until you hit this point, and then it goes from here to there. So if we set it up dx dy, we have to split it up into two pieces, right? X varies from here to the line until you hit that point, and then it's from the y-axis to the circle. So dx dy, you're going to have to split up into two pieces. Dy dx, though, you're always going from the line to the circle. It's always from the line to the circle. From the line, y equals x, to the circle, right? Here, y is plus or minus square root of 4 minus x squared, but the top is just the positive. So from the line to the circle, and then you project onto the xy plane, and what do you get? Yeah, the interval you get will depend on this point of intersection. When x is equal to y, you get y squared plus y squared is equal to 4. So 2y squared is equal to 4. Y squared is equal to 2. Y is plus or minus root 2, but of course it's the positive here. And when y is root 2, then x is root 2 as well. So x is going to go from 0 to root 2. All right. And the integration with respect to y is very easy. So let's do it. If you integrate with respect to y, that's 2xy minus 1/2 y squared. Do we want to clean that up? We have a minus 2 and a plus 1/2 x squared, plus 1/2 x squared, that's x squared. Minus 2x squared is going to be a minus x squared dx. And this is easy to integrate. That's trivial, that's trivial. And here, because of the x, this is easy. You can make a simple u substitution. I'm sure you can integrate that in your heads. What do we get? Minus 2/3. 4 minus x squared to the 3/2. Minus 2x minus 1/3 x cubed. So 2, 4, 8, 16. And there you have it. Oh, I know what you're thinking. Where did we use polar coordinates in this? We didn't. You don't have to use polar coordinates. Polar coordinates are only there to help you. This was very easy to do without polar coordinates. So we did it without polar coordinates. Where does the minus come from? From the chain rule, the derivative of the inside. Or if you make a u substitution, make a u substitution. U is 4 minus x squared. So du is minus 2x dx. Or, work backwards, if you differentiate this, the derivative of the inside is negative. So you need a negative outside to compensate. Right? But the point is, we didn't use polar coordinates here because everything was easy and we didn't need to. let's redo this question now in the context of polar coordinates. It's not going to be any simpler because this was very easy, but at least it'll give us a chance to verify our answer and see how polar coordinates may be used if you wanted to use them. Is this answer correct? Well, we'll see. We'll see because we're going to redo it using polar coordinates anyways. Let's redo this question in the context of polar coordinates. You know what the polar coordinates are. X is r cos. Y is r sine. Jacobian r dr d theta. Now what you want to do is describe this region in polar coordinates. What is that region in polar coordinates? How do r and theta vary in order to describe every single point in this shaded region? Well, I mean, this is the circle of radius 2. So you see, if you take a ray of length 2 and you rotate it around, right, you see what's going to happen. If you have a ray of length 2 and you rotate it around, you're going to touch every point in that region. So if you take a ray of length 2 and you rotate it, starting on this ray, which is, right, the line y equals x, which corresponds to theta equals pi over 4, right? Because in polar coordinates, this is r sine equals r cos. The r's cancel out, or sine is equal to cos. When r, sine, and cos equal? When theta is pi over 4. And it goes all the way to 90 degrees, pi over 2. And when it's asking why is it r dr d theta, what did you want it to be? Right? Don't forget the Jacobian. Jacobian is r dr d theta. I don't have absolute values because I'm going to make sure r is positive, right? And if r varies from 0 to 2, and then, so r varies from 0 to 2, theta varies from pi over 4 to pi over 2, I will have touched every single point in the shaded region. Multiply that out. This is 2r squared cos minus r squared sine dr d theta. Why does r go from 0 to 2? You want to touch all points. If r was 2, you would just have this thing here. Right? I mean, you want to describe all points in the shaded region. Right? So if R is 1, you have this. If R is 1.5 or 1.3, 1.5, 1.7, right? So in this way, you're going to describe every point in that region. Integration with respect to R is trivial. I mean, I've rubbed it off now, and I should not have, but I'm sure you've taken down the answer. Integrated with respect to R, that's easy. 2 over 3 R cubed minus 1 over 3 R cubed from 0 to 2. What do we get? 16 over 3 cos minus 8 over 3 sine. Integrate again. Antiderivative of cos is sine. Antiderivative of sine is negative cos, so that becomes a plus. From pi over 4 to pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Subtract sine of pi over 4 is 1 over root 2. And cosine of pi over 4 is 1 over root 2. Or root 2 over 2 if you prefer. Let's do that. Root 2 over 2. Root 2 over 2. And what do we get? 16 over 3. This is minus 8 minus 4 is minus 12. Minus 12 root 2. Is that what we had? 8, 9, 10, 11, 12. I don't see it anymore on the board. I'll assume that's what we had. Unless otherwise. Why is R positive? Well, look at how R varies. R goes from 0 to 2. So it's only taking on positive values. We had 8 root 2 instead of 12. Yeah, I seem to recall we had something slightly different, right? What, have I made a mistake anywhere? Where's, anybody see? Thank you. Does anybody spot the mistake? Well, that's an unfortunate. Nothing yet? No. All right, well, I don't want to waste too much time figuring out a mistake. Let me quickly redo it. I see my mistake. When I plugged in root 2, I assumed this was 0. It was not. No, it was a mistake in here. Yep. When I plugged in root 2, I assumed it was 0, when it clearly is not. So I was missing a minus 2 over 3 times 2 root 2. So I was missing a minus 4 root 2. There it is. This is the right answer. Yeah, it was a mistake in the previous example without polar coordinates. I was missing what you plug in 0 and root 2. I plugged in root 2 in my head and I thought it was 0, but it wasn't. Yeah, there it is. Sorry about that. Go ahead and fix it to the previous example. Everybody understands what I'm talking about, right? We have this as one part of the antiderivative. When you plug in a root 2, you don't get 0. For some reason, I mistakenly thought it was 0.